Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on February 24, 2026, exactly 1 week ago. It introduces a new framework called Adaptive Edit Chain of Thought, which achieves better image editing performance while running more than twice as fast as the standard best of n baseline. The paper is titled, From Scale to Speed, Adaptive Test Time Scaling for Image Editing. And as we'll see later, the shift from brute force scaling to intelligent resource allocation has some significant implications for making generative models more efficient. To understand the motivation, Figure 1 illustrates a key distinction between generative tasks. The top panel shows that text-to-image generation is open-ended, so generating many samples is beneficial because it yields diverse options like different cat poses. However, the bottom panel highlights that image editing is fundamentally different. Since the output is constrained by the source image, blindly scaling up samples often just produces redundant copies, which means traditional scaling strategies waste significant computation. Figure 2 details exactly why standard scaling is suboptimal here. Panel A shows that fixed budgets are inefficient because simple edits, on the right, see almost no improvement from extra compute, while only the difficult ones on the left truly benefit. Then, Panel B exposes a major risk in early verification. The data shows that 40% of samples with low initial scores actually become high-quality final images, which means standard pruning methods would incorrectly discard valid solutions. Lastly, Panel C illustrates redundancy. The high green bars indicate that when an edit succeeds, it produces multiple correct copies, implying we can stop generating as soon as we find the first good one. So Figure 3 brings these insights together into the proposed framework, contrasting it with standard methods. The top panels show the baselines. Best of n simply generates everything at once, while standard early pruning tries to filter candidates, but often relies on generic scores. In contrast, Panel C maps out the new Adaptive Edit Chain of Thought pipeline. It starts on the left with a difficulty-aware budget, which dynamically sets the sample count based on task complexity. Then, the blue section performs edit-specific verification, using quick previews to catch errors like wrong regions early on. Finally, the green section demonstrates depth-first, opportunistic stopping, where the model finishes the best candidates one by one and quits the moment it gets a good result. Alright, having seen the pipeline, Table 1 now presents the quantitative proof. This table compares adaptive ADE-CoT against state-of-the-art methods across 3 different models: Flux 1 Context, Bagel, and Step 1x. Edit. The columns track performance on benchmarks like G-Edit Bench and any edit test. If we focus on the top section for Flux 1, the proposed method, labeled ADE-CoT, consistently achieves the highest scores, which are marked in bold. But the most important result sits in the speedup rows at the bottom of each block. For instance, on G-Edit Bench, the method delivers a 2.2 to 5.5 times speedup over the best of n baseline, effectively cutting computational cost while still improving quality. So, while Table 1 gave us the snapshot numbers, Figure 4 plots the full scaling trajectories. Here, we track overall performance on the vertical axis against computational cost on the horizontal axis across the 3 models. The blue curve represents the standard best of n baseline, serving as our reference point. But notice the purple line with star markers, which tracks the adaptive edit chain of thought method. It consistently sits above and to the left of the blue line, meaning it reaches higher quality levels with significantly fewer function evaluations. Well, to understand exactly what drives these results, Table 2 breaks down the contribution of each strategy. It tracks generation quality, GO, and computational cost, NFE, across the 3 models. Starting from the baseline, Row A shows that adding difficulty-aware budgets immediately reduces the function evaluations, for instance, dropping from nearly 900 to roughly 800 for the context model. Next, Rows B through D reveal that early pruning and filtering slash the compute cost further by removing poor candidates. Finally, the bottom section demonstrates that the instance-specific verifier and opportunistic stopping are crucial because they actually boost the quality score while maintaining that efficiency. Wrapping up, 2 takeaways stand out. Treating image editing as a goal-directed task enables much smarter resource allocation. By dynamically adjusting budgets and stopping early, this method achieves high-fidelity results while halving computational costs. It suggests a major shift from brute force scaling toward efficient, adaptive inference. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.